There are three output formatters. The first is the table formatter. This takes a list of numbers and formats them as a text-based table. Do you remember that we specified in G1 that the output should contain 32s, 43s and 35s, so 100 numbers in total? In the table formatter we can specify the input list as G1 and specify that they should be laid out horizontally in 10 columns here. And that's what you'll see, a 10-column table as described. We can change that to vertically in 20 columns. And then you can see those same numbers laid out in a different way. The layout of the numbers is they are separated by tabs with each row ended with a paragraph or a carriage return. That means we can copy these and paste them straight back into Excel. The second formatter just below the table formatter is the graphics formatter, but I'm going to go past this at the moment down to the animation zone because that's the simplest graphical formatter. The animation zone simply takes a list of numbers and displays them as coloured cells in a grid. The size of the grid is determined by the size setting from 10 by 10 to 150 by 150. If we set this to 10 by 10, we can now specify values to be fed in as input. Now, I wouldn't normally insert values in this way, but we can insert them directly into the cell formats field. And I've already put in here 100 5s laid out in a table. Laying them out in a table helps you to see what the numbers are and where they're going to be. So if I now press equals, you can see that I get 100 blue squares. I'm just going to change a couple of these now. So if I change this first one here, top left corner, to a 3, and I change the bottom right corner value to an 8 and press equals, then I get a red one in the top left and a yellow one in the bottom right. How does this work? Well, the numbers 1 to 20 each specify that the associated cell should have a certain format, a particular colour with a border. You can see the colours that 1 to 20 map to by going to the top and clicking on the codes link. But we can do so in a different way by changing the numbers at the top here. So if we put in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then pressing the equals button, we can see that we get white, black, then 3, 4, 5 are red, green and blue. 6, 7, 8 are magenta, cyan and yellow, and 9 is grey and 10 is orange. Most of the many apps that come with Numipulator use only the colours associated with the numbers 1 to 20, so you don't need to learn a large number of colour codes. There are, however, many other codes that give millions of shades, which we won't cover here in any detail. Now, you may remember that we generated 100 numbers, 33s, 41s and 35s in box G1. We can replace the numbers we've just entered as input to the animation zone and replace it with G1. Let's do that. Now when we press the equals button, we get 3 bands of colour: red, white and blue. Now that looks a little like the Netherlands flag. However, a flag doesn't normally have squares all over it. So we can remove those, and I'll show you how we do that. We can move up to rows V and W, and we will put in here G1. No, let's put it in this one. It's already selected. I want to change the sign. I want to effectively multiply all the numbers by -1. So I'll put in G1 there. We've now got W3, which will have, instead of the 30 ones, it will have 30 -1s and so on. So we come down here and we put in here W3. And now we see something that's more like the flag of the Netherlands. And that's because every minus number has no border. So if it's a positive number, it has a border. If it's a minus number, it's the same color, but it has no border. I come to the top of the Numipulator, and I'm going to press the codes button, just so that you can see all the 20 colors that are basic to Numipulator. In addition, 0 is a black square without any border. So in that sense, it's like -2, which also gives a black borderless cell. I would just like to mention some other codes. So I've gone down to row G, and I'm going to select here random integers from P2 to P3, and so I'm going to ask for 100 of those from -1 to -1000 to -1999. Now those values, -1000 to -199, give you exactly 1000 different shades with borderless cells. So if we go down to the bottom now and put in here G4 and press equals, we get that. So you can see a lot more different shades than you had with just -1 to -20. The way these codes work is that it's only the last 3 digits that are really important. You still need the 1 or the -1, but something like 1462 means that you will get 4/9 red intensity, 6/9 green intensity, and 2/9 blue intensity when the colors are combined to give the color that you see in the cell. So if we look at 1900, that means we've got 9/10, in other words 100% red, no green, no blue, so you will just get out red from that. An important feature of many apps is the repetitions feature. So far we've seen that if we press the equals button, a set of calculations is carried out and the answers displayed, including the graphical output in the animation zone. This is called cycle. Now many games and apps depend on having many cycles, one after the other, sometimes even with no user interaction. We therefore need repetitions of cycles. There is a small area called repetitions where we can specify the repetitions we want. So we'll move up to there now. The type of repetition is always a repeat until. That is, we specify that repetitions should carry on until evaluation results in a specified termination condition succeeding. So let's go up to the top and specify that A1 is going to be a random number between 1 and 50. So here we are, random integer a to b, and we'll come back down again and we'll specify a terminating condition. I'll find it in a minute. Right, so here I'm going to say repeat until a1 equals 1. Now, we normally press the start button rather than the equals button to start a set of repetitions. That's because the equals button only ever gives you one cycle. So we'll press the start button, and you'll notice over there it said the cycles when it stopped were 20. Press it again, and this time it's given us 79. Now let's go down to the animation zone and press start, and we will see a whole set of different screens, each with a different set of colors on it. That's because G4 produces random integers between -1000 and -1999, so that changes every time. Now, for some apps, we want repetitions to carry on without end. So if we go up here, and we can change this and say repeat until 2 equals 1. Now that's never going to be achieved, so if we press start now, we can see that we're getting all these cycles going on and on. We might as well move down and just show that that's continuing down here. And then stop. I didn't mention there that to stop the repetitions, you press the stop button over here. Now, that screen was changing very quickly. So if you want to slow things down a bit, you can specify a delay between cycles. So if I put in here half a second display, 0.5 seconds, go down here and press this again, I will do start. And now you've got something that's more likely to be the speed you want in a game. Probably something between 1/10 and half a second. And we'll press stop. When you're designing games for the animation zone, you'll need to make use of the keypad on the right, as this is the only way in which a user can interact with it. You'll usually use the arrow keys to move an object in a particular direction. You might use the diagonal keys also to rotate, and maybe you'll use the red central button to shoot or to jump. The arrows on the keypad can be changed to other symbols very easily by declaring things in this area, but I'm not going to go into that now. Now, Numipulator comes with a simple demonstrator that you can adapt for your own purposes. To load this, we need to look at how programs are loaded and saved, which is just below the animation zone, in an area called Input Output Numiplets, down here. Loading and saving of programs is done via Numiplets, which consist of all the inputs, selected functions and settings wrapped up in text form, together with the title and description, the fields for which are also found in this area. So here, if I wanted to put a description in here, I can do. This is rubbish, and this is just a demo that we can put in here. And if I now press the create button, that creates all of this in text form. You can copy and paste this text into a text document, such as in Notepad on a Windows PC, and save it. Then to reload it at some future time, you paste the saved text into the input text field here and press the Load Numiplet button. Now, what I'm going to do is paste in a Numiplet I've got from another app. So if I paste that in here, Control V, and load it, you'll see that this has actually created or loaded a digital clock app. When it loads a new program from the Load Numipulate area, it also backs up your existing program into the output, so that's actually been re-output into that area, so that in case you want to save it. Your program is also saved in local storage whenever you close Numipulator, and when you open it up again you should find that your last program is automatically loaded. So for example here, if I just reload Numipulator here, it loads and I've still got the digital clock app here. Let's just go up and look. Yeah, it's now going. Now there's also a save button that puts your program into local storage, and it's worth tapping this occasionally over here, just in case you shut your browser without closing Numipulator, as this may not save your program. So I think if you just shut the window like this, clicking on Numipulator there, it will go away and it will save it. But if I accidentally just go over here and click on the go away button, it may not save it, or if it gets shut in some other unusual way. Numipulator comes with many built-in Numipulates or programs or apps which can be loaded and the programs inspected and used. One of these is a small demonstrator of controlling an object using the keypad in the animation zone. To load a built-in Numipulate or app, we go down here and select it from a drop-down list. Realize you can't actually see that, so I'm going to choose keypad control to move object. I then click on this yellow button here to transfer it into the input box as we did before, and now we can load it. The program starts automatically, so you won't see anything moving at this stage, but if we go up to cycles up here, you can see it is running, it's increasing all the time, and we can move the object around using the keys. So we can use those keys there, and so on. The code for this is designed to work with different shaped objects and different sized grids and different speeds. So if we move up to rows D and E, we can see how much it moves with each press of the key, the object height, the object width, the board size, and those are the object formats there. So you would be able to change those to move your own objects around. We're now at the other graphical formatter called the graphics formatter. This is more complex than the animation zone. One key difference is that it has no keypad, but instead users can tap directly on the cells to interact with the game or puzzle. The other key difference is that it takes two lists of numbers as inputs, that's that one and that one, as well as having a field that specifies the number of columns in the table of cells to be displayed. One of the input lists is again cell formats. All the formats that were used in the animation zone can also be used here. So if you have a 3, that again specifies a red cell with a border, and -5 specifies a blue cell with no border. The other list, LA, is the table of values, and these specify the numbers that will be displayed in small white fields in the cells. These are small text fields. Before we start to use this, let's first of all clear out whatever programs we've got in here by pressing on the clear button. Now this does ask me whether I'm sure about this because it will delete data. I'll press OK. Incidentally, it will save it anyway. It will save it to that output area that we saw before. Let's go up to row G, and a bit like we did with the animation zone, first of all we will generate the integers 1 to 100. Let's do that in G2 as it's already selected. And we will do random integers in this one from 1 to 20. So we'll do 100 random integers from 1 to 20. And so we've now specified G2 and G4. We'll go back down and we'll put G2 in as the table parameters. We'll put 10 in as the number of columns because that's the default here, and we'll put G4 in as the cell formats, and we'll press equals. So here you see the numbers 1 to 100, the values in LA, displayed in the middle of the cells which have colors as defined by the random numbers generated for G4. Now many of the apps or programs that you'd want to produce will include displays of letters or words. We'll look now at one way in which the interface can show these, and this is through output mapping. Just below cell formats fields is one called cell text. In this we can enter simple, mainly self-explanatory mappings from numbers to text. So if we put in here equals 1, hello, equals 2, world. We do use colons here to separate the numbers or the check and the text that's going to be used. Then we might have less than 11. That will make nothing. Let's just leave that as blank. Less than 30. Small. Less than 40. Medium. And less than 70, large. Now we press equals. So we can see that where there was a 1, we now have the word hello. Where there was a 2, we've got world. From 3 to 10, we've got just blank because there's no text. So it's still text, but it's blank. And then we've got a lot of others called small, then we've got some medium, then we've got large, and then we didn't specify what happens for 70 and over, so they're still left as numbers. Let's just change that in one way and add on here n, which means any number that's left will be no text. Now no text means it will not display text, and it won't even display the white field. So now if we press equals, we see that those fields at the bottom have no field in them, and they're just displaying the colors, which can be very useful. Notice the difference between no text, where there's nothing displayed in the middle, and just blank up here, where you still get the white text field. Now these checks in cell text are carried out in order. So as soon as it finds a value that replies to that particular number, it will stop. So if I now change n no text and put it at the beginning and press equals, all the other ones will be ignored, and we then just get cells with color only, very much like we had with the animation zone. Code 0 and codes -1 to -20 have the same color as they do with the animation zone and are also borderless as they are with that. In the graphics formatter, there's a difference between 0 and -2 as codes, both of which are black and borderless, and I'll show you the difference by putting in here in G1 to generate 50 zeros and 50 -2s. And we'll go back down. We'll enter the cell formats as G1. We'll remove all this in here and press equals. And you see the difference that 0 is borderless and black but doesn't show the white field, whereas -2 is also black and borderless but does show the white field. So 0 is intended as background. It never displays anything. So with code 0, the associated value from the list in LA up here is clearly being ignored. And the same is true for many other format codes concerned with displaying symbols, shapes, emojis, and other images. There is a class of format codes that take the form NFGBG, where N is a 1 or 2 digit number from 1 to 99, and FG is a 2-digit number from 00 to 20, as is BG. Now, FG represents the foreground of an object, and BG represents the background color of an object, whereas N represents the type of object you're displaying. As you probably expect, the numbers 0, 1 to 20 represent the same simple color codes as before, so going from white, black, in fact through to beige, and 00 is black. Most of these codes, except for n equals 18, 19, and 20, ignore the associated value. If n equals 1, for example, the object to be displayed is a small filled circle, so the code 10305 specifies a small red filled circle on a blue background. Now, with the graphics formatter, we can display a single cell. So let's start off by putting the value 68 in here as the single value. The number of columns is going to be 1 because there is only one column, there's only one cell, and we'll put the format here as 10305, and we'll press the equals button. And now you can see that we have just that one cell, and it's a red circle on a blue background. If I change this to 40609 and press equals, then I get a magenta square, a small one, on a grey background. 80408 gives us a yellow background with a green down pointing arrow on it, while 140300 gives us a red heart on a black background. Now we can see all the objects by going to the codes display up here, as we've been before, where we had the color codes. But further down we've got what these numbers mean, the value of n. So you can see 1 is a small circle, 4 was a small square, and 14 is a heart symbol. And then if we move further down beyond 18, 19 and 20, then we can see that the numbers 21 to 28 are various arrows, 29 is a full stop, 30 to 40 are the numbers 0 to 10, 40 to 66 are the letters A to Z, and then there are various other symbols going up to 98 and some words as well at the end there, and 99 is just a blank. The value of n equals 99 is actually quite interesting because it means that we can come here and we can put in here 99 0406 and press equals, and we'll see that the foreground color is ignored because it's a blank, and we just get the color 06, which is magenta, displayed. Now we missed out looking at codes n equals 18 to 20, so we'll return to those now briefly. These ones do take account of the associated value, which is set to 68. Now I'm just going to add something here to remind me why I've done 68, and I'm going to add in a comment. You can put comments into any input, and I'm just going to put in here ASCII D, so saying that that letter is the ASCII code for D, and that will come in useful in a minute. Comments are always placed between curly brackets, also called braces. Now if I go down here and change the value of n from 99, which meant display nothing in it apart from the background color, and I change it to 18, then what I get is the letter D being displayed. It's in green on a magenta background. So that's the 04 is green, 06 is magenta. We've now shown 3 ways of getting letters to be displayed on the graphics formatter. One was the output mapping using cell text. The other one was by using values of n between 40 and 66. And the other one is to use this code 18, value of n equals 18, and to put in here ASCII codes that represent letters. If I change the value up here to be minus 68 and press equals, I get a smaller D displayed. Now that can be quite important for some of the Unicodes because they also include emojis, and some emojis have to be at the smaller size to fit into the box. I'll give you an example of that in a minute. So if I change the value up here to minus 127773, you don't need to remember these by the way, which is no longer ASCII D, so I'll remove that comment. Then you get the value, well, you get a smiley being displayed. And if we change it again to minus 127826, then we get some cherries. So you'll find that many of the emojis are up at that level of Unicode, minus or 127 something. If you're wondering how to find out the Unicode codes for symbols, characters and emojis, there's a built-in app that lets you see the symbols and their codes. I'm going to try to load that now. So I'm going here, and it's this top one here, Symbol Finder. So I will put that into the input area and now load it. And we will find that this is in the graphics formatter. So what you see here are the symbols for codes 1 to 100. Now I know that down here, no, up here, it says to try 1277 in here for emojis. So I'm going to do that. And then I'm going to press the start button. And now when I go back to here, we start to see emojis. And to find a particular code, we click on the one we're interested in, like this palm tree here. Click on that and we look at the top and it tells us that it's code 127796. You may remember we mentioned the cherries one before, so if I click on here, that's where we get 127826 as the code for that. You can also search for a particular code online. You might put in something like cherries emoji code and you should come across that. Look out for the decimal code. All right. Use of this app also demonstrates a key feature of the graphics formatter, which is that the user interacts with the display by tapping or clicking on a cell. And this will trigger both another cycle and any display change. Now the display change or action is derived from three numbers. Basically, the row last tapped, which is called graph in 1, the column last tapped, which is graph in 2, and click, which is an internal value that is 1 if a cell has just been tapped or 0 otherwise. To demonstrate this, I'm going to change the feedback values, which are currently, these ones here are currently determining what appears up here, and I'm just going to change those to be graph in 1, graph in 2, and click, the values we just mentioned. So if I click on this ice cream here, you can see that it says I've clicked on that the row is 5, the column I've clicked on is 1 and 3, and the click is 1 to show that I've just clicked on it. If I click on this wine here, it then changes to 731. Now, if I now go to another page without clicking on any of these cells, it will still say 7.3 up there for the that was the column I last pressed on. Sorry, the row I last pressed on. That's the column I last pressed on, but I haven't just clicked on anything, so that is now 0. The value of click is crucial when determining displays or actions. In this particular app, a value of 1 causes the selected cell to be highlighted, while 0 displays the next page of symbols or emojis.